Today's lecture is on solving quadratics, and this is the third method that we're going to talk about, and it is called completing the square, and it will work for any quadratic. I'm going to walk through the process, and then I'm going to explain exactly why it works after I kind of walk through it once. Okay, so my first example here is x squared plus 4x minus 5 is equal to 0. Okay, so the idea of completing the square is actually to turn one side of the equation into a perfect square. In the previous lecture on using the square root method, we had things that look like x plus 7 quantity squared is equal to 9. And we could use the square root method to solve that. We would just take the square root of this side and this side, put plus and minus, and I would have x plus 7 is equal to plus and minus 3 in this case. And then I can subtract the 7 from both sides, and I get x equals negative 7 plus and minus 3. So this gives me x equals negative 7 plus 3 and x equals negative 7 minus 3. So that's the square root method. And our job today for completing the square is actually to turn this equation into something that looks like this. Okay, so we do that. So this is normally whenever we see a quadratic, the first thing we typically do is set it equal to 0. This is the one time when we don't. And so what we're going to do first is we're going to actually move the constant term. See how the constant term is over here on this one? We're going to move the constant term over there. So I have x squared plus 4x. I'm going to leave a plus and a blank here. I'll explain that here in a second as to why I'm going to do that. And then on this side, when I add 5 to both sides, I get 5, and then I'm going to put plus blank. So I'm leaving these blanks to remind myself that I'm going to add something to both sides of this equation, because whenever I'm solving equations, I can only do something. I can't do something to one side. I must do it to both to make it equal, because the equal is a balance point. Okay? So I want to figure out a way to make that left-hand side a perfect square, because this is the side here, right? The constant is here, that's the 5, and then this side here I want to be a perfect square. Now, so I need to add something to it. It's always going to be plus. Again, I'm going to show you exactly why it's always going to be plus in just a second, okay? So the way that we figure that out, okay, so let me point out a couple things. First of all, this method only works when the leading coefficient, I've touched on this before, but the leading coefficient is the number in front of the highest power of x, which in this case, it's implied it's 1. Completing the square only works when that number in front of x squared is equal to 1. If it's not equal to 1, then we have to do an extra step before we can go forward. And again, when I explain why this procedure works, you'll see why. So the way that we do this, the actual technique, is we take the number in front of the middle term. This is the x term. We take this number 4 here, and we're going to divide it in 2. Okay? So when I take 4 and divide it by 2, I get 2 back. So what I'm going to do with this number is square it then, right? So normally, let me write it this way. If I have ax squared plus bx plus c is equal to 0, right? And I'm going to assume when a is 1, then what I have here is x squared plus bx plus c equals 0, okay? So the general rule of thumb is, well, first I'm going to I have x squared plus bx, and then I have a plus here, is equal to negative c plus something. I'm going to take, in general, I take this number, which is b, I'm just holding a b because it could be any number, I divide it by 2, and I square it. Okay, this is the number, then I'm going to add this to both sides of my equation. This is the number. Add to both sides of equation. So in 2 squared up here, that's what I've done here, that my b is 4, I'm dividing by 2 and squaring it. I get 4 again. It's a pretty boring example, but so I get x squared plus 4x plus 4 is equal to 5 plus 4. So let's simplify the right-hand side because that's just a number. So I have x squared plus 4x plus 4 is equal to 9. So I'm hoping, if I did my job correctly, that this left-hand side will factor into a perfect square, right? So we're going to factor the left-hand side. I have x squared plus 4x plus 4, and then I have x plus 2 times x plus 2, if you notice. So I have x times x gives me x squared, and then this is 4, right? And this is plus, so both my signs match this sign. And then I have 2 times 2, which is 4. So this is how, if I check, I get 2x here, and I get 2x here, and I have x squared plus 4x plus 4 in the middle here. So I can write this now, because I have x squared times x plus 2 times x plus 2 as x plus 2 quantity squared is equal to 9. Oops, let me move up my paper and then you can see it. All right, so now we have the same situation as we had up here. And so now I just take the square root of both sides. I have x plus 2 is equal to, I'm going to take the square root of x plus 2 squared, is equal to plus and minus the square root of 9. Okay, so when I take the square root of something squared, I get back what's just the one thing. I get x plus 2 is equal to plus and minus 3. Oops, I'm really struggling here. So now I can move my 2 to the other side, so I subtract 2 from both sides. I get x equals negative 2 plus or minus 3. And so I get two distinct values. Now when I have a radical in there, you can just leave it as a radical, but when I get integers or fractions, right, if I get numbers without a radical, then I should go ahead and simplify them. So I get negative 2 plus 3 and negative 2 minus 3. So this gives me positive 1, this gives me negative 5. So I have two values for x that will solve my equation. And that's how we complete the square. So let me explain why, first of all, my x squared has to have a leading coefficient of 1 and why I'm always going to add to both sides. Okay? So let's take an example here. I'm just going to use a vague general term here. I have ax plus b times ax plus b, right? This is what we call a perfect square, right? So exactly the same thing multiplied by itself. I could also write this as ax plus b quantity squared, okay? So let me multiply this out, okay? So I have these two, my first two terms I'm multiplying together. I get ax squared, a squared x squared when I multiply them together. I get a outer term of ax times b, so I get axb. And then I have an inner term also of axb. And my last term, which is the b times the b, is b squared. So I have a squared, x squared. These two things are like terms. I'm going to write them in a slightly different order here. I'm going to write, usually we write the variable last, and a and b are just numbers. So we're going to write a, b, x, and there's two of them. Okay? So I have 2abx plus b squared. Okay? Now you notice I said that a had to be always 0. That's my leading coefficient. So if I plug in when a is 1, then I get x squared, because I get 1x squared, which we don't write. And then here, the a is 1, so I'm just going to be left with 2 times 1 times bx. So I'm just going to write 2bx, and then plus b squared. All right. Notice this last term is always a plus. Let me just show you with the minus as well. A perfect square could look like this, right? And by using basically the same general thing, I'm going to get a squared, x squared. This time, both my middle terms will be minus instead. That's the only difference. So I'm going to have 2abx plus b squared. And again, when a is 1, then I get x squared minus 2bx plus b squared. So you notice in both cases, this is a good explanation as to why I'm going to always add, because when I multiply two perfect squares together, then I'm always going to get a plus as my last thing. Okay, it doesn't matter if they're both minuses, it doesn't matter if they're both pluses. A negative times a negative gives me positive, and a positive times a positive also gives me a positive. So that's the explanation for that. So the other part was that we added b over 2 and we squared it to both sides. Okay, so we do that because here is that term in front of the x. In our case, we have 2b. And so I have b squared, so I need to know how to get b squared. Well, in order to get b alone, of course I would divide it by 2, right? That's going to give me b, and then I square it. And so that's how I end up with I take that middle term, I divide it in half, and I square it. But again, I want to reinforce that this only works when your a term is 1. Otherwise, if I have minus 2ab in this particular case here, and I divide by 2, right, then I get something different, right? I'm going to get 2a in there. And so this only works when I have a leading coefficient of 1. Okay. So let's look at how we go about solving one that doesn't have a leading coefficient of 1. We just have an extra step. We can still do it, it's just not as fun. Okay. So I have 2x squared plus 5x minus 8 is equal to 0.
Having trouble with the connect.
Okay. And so I have this particular problem. I want to complete the square. Now, really, if anybody gave me the choice of what method to use, this probably wouldn't be it, okay? Because it's not going to be pretty, right? But we can still do it. It's still doable, okay? So the first thing that I noticed is that my leading coefficient is not 1, and so I need to force it to be 1. So I'm going to divide all of my terms by 2, including the 0. That's going to leave me with x squared plus 5 halves x, and then I'm going to have minus 4 is equal to 0. All right, I know that I need the constant term on the other side, so I get x squared plus 5 halves x, and then I have plus a blank is equal to, I'm adding 4 here, and I get 4 plus a blank, okay? So, all right, now I'm ready to add something to both sides to make the left-hand side a perfect square. So I take my middle term, I get 5 halves, I'm going to divide it by 2 and then square it, okay? So when I divide by 2, right, it's really the same thing, right? 12 divided by 2 is 6, and 12 times a half is 6. So really, dividing by 2 is like multiplying by a half as well. So I can think of it like that, 5 halves times 1 half, and then I'm going to square it. So this is 5/4, and then I square it. So what I'm going to add to both sides is 25 over 16. Okay, so I'm going to do this here, and I'm going to have that here, because I always do the same thing to both sides. Now it's important that I remember this because it's actually going to help me out a little bit, so I don't have to work quite so hard. This is going to factor into x, right, and x is equal to 4 plus 25 over 16. I'll combine those later. I'm just going to bring them along for right now. And I have a plus, which I will always have, so that means my signs match, and they always match this first sign, so I know I have a plus plus, right? And then I know that this should factor into a perfect square. So basically these both need to be identical. So 5 times 5 will give me 25. I know the 5 will go on top, and 4 times 4, that's my perfect square. You notice 5/4 here? What this ends up being is x plus 5/4 quantity squared equals 4 plus 25 over 16. Okay? Now we have a little bit more work to do here. So let's clean up the left-hand side, or the right-hand side, I should say, and let's make this into a common denominator. So I have x plus 5 over 4 squared is equal to, this is really 4 over 1, right? And I want it to be 16th, so I'm going to multiply 4 over 1 by 16 over 16 to make the same denominator. Okay? All right, so I have x plus 5/4 squared is equal to, this is the 25 over 16. I get a plus and a 16 on the bottom. All right, so I'm going to end up with 64 on top, right? Because 4 times 16. 4 times 6 is 24. I carried the 2. I got the 64. And so now I have the same denominator, so I can clean it up a little bit more. And so 64 plus 25 is 89 over 16. And now I have it exactly the way I want it. I have something squared equals a number. So now I can use my square root method. I put my plus minus here. I get x plus 5/4 on this side is equal to plus and minus the square root of, I'm going to put the 8, when I have a fraction, I can take the square root of the top and the square root of the bottom. It's going to make my life a little bit easier because 16 is a perfect square. So I'm actually going to pull that 16 out of the radical and just call it 4. That'll make it a little bit easier because if you notice, this also has a 4 in the denominator. So in my last step, I want to get x by itself, so I'm going to subtract 5/4 from both sides. And I get x equals negative 5/4 plus or minus the square root of 89 over 4. Okay? Another alternative way that I can write this is x equals, since they have the same denominator, negative 5 plus or minus the square root of 89 over 4. These are both equivalent expressions, and there gives us two distinct solutions in both cases. I get negative 5/4 plus the square root of 89 over 4 and negative 5/4 minus the square root of 89 over 4. So if I was going to decimal approximate that, I would need to put both of those separately into my calculator. All right, that completes the completing the square lesson.